good morning. Welcome you all to the lecture on hierarchical control techniques in hybrid AC-DC microgrid. Before going into this topic, I would like to explain you all briefly the fundamental basics required to study the hierarchical control techniques in hybrid AC-DC microgrid. As explained in the previous lecture, the smart grids are the next generation power systems which houses the renewable and energy storage systems at distribution system level in the form of microgrid. The microgrids are synthesized to operate in grid connected and standalone, that is islanded mode, enhancing the reliability of the system. The vital power generations integrated in the microgrids are wind, solar, microhydro, biomass, geothermal, tidal energy, fuel cells, diesel generators as well as energy storage. Of all the types of microgrids, hybrid AC-DC microgrids emerged as feasible configuration due to its advantage such as minimal power conversion ability to integrate both AC and DC sources and loads. The typical configuration of hybrid AC-DC microgrid is shown in the figure. The hybrid AC-DC microgrid comprises of AC and DC subgrids integrated with AC and DC type sources and loads. The AC and DC subgrids are interconnected with a bidirectional interlinking converter. The components in a hybrid AC-DC microgrid are segregated as physical component and communication infrastructure. The physical component include power sources, loads and power converters in the AC and DC subgrids, controllers and sensors. The communication infrastructure includes communication network, intelligent electronic devices and communication protocol such as IoT for the network connected hybrid AC-DC microgrid. The types of converters integrated in hybrid AC-DC microgrid are unidirectional power converters to transfer power from renewable to respective subgrids. The interlinking converter integrating DC subgrid and AC subgrid is segregated into two categories. First one, bidirectional interlinking converter, which is a single stage 3-phase inverter generally operated to equalize AC side frequencies and DC bus voltage. Second, the other type is back to back bidirectional interlinking converter, which is a dual stage converter with 3-phase inverters connected back to back and operating in a constant power mode with reference to respective buses. The structure of hybrid AC-DC microgrid are segregated into various types such as AC coupled hybrid microgrid, DC coupled hybrid microgrid, AC-DC coupled hybrid microgrid. The AC coupled hybrid microgrid houses various distributed generations, so called DGs, and energy storage connected to a common AC bus through interfacing converter. Similarly, in a DC coupled hybrid microgrid, the distributed generations and energy storages are connected to a common DC bus to interfacing converter. However, in a AC-DC coupled hybrid microgrid, distributed generations and energy storages are integrated to respective AC and DC buses, which are interconnected by an interlinking converter. With this fundamental knowledge, let us look into the key features of hybrid AC-DC microgrid. The key advantage with hybrid microgrids is the ability to operate in grid connected and islanded mode autonomously. The other advantage is that hybrid microgrids are generally operable on droop control. The equivalent power sharing among AC and DC subgrids prevails as a crucial problem while opting for droop control. Why do we need energy storage in hybrid microgrids? Due to the intermittent nature of renewable energy resources and other energy sources, the storage elements are critical part to enable the stand-alone operation of microgrids or to smooth the microgrid power flow during grid connected operation. The storage elements can be classified into two categories: capacity oriented energy storage and access oriented energy storage. Capacity oriented energy storage does not have fast response time and they are used for long term energy balancing to buffer out low frequency power oscillations of distributed generations output power and compensate intermittency of renewable energy sources in a microgrid. Batteries, pumped hydroelectric systems, compressed air energy storage and hydrogen storage are types of capacity oriented energy storage. Access oriented storage devices have fast response time and they are responsible for short time disturbances in microgrid. By providing the high frequency component of power, they can supply or observe the high power transients with high power density. Flywheels, supercapacitors and superconducting magnetic energy storages are considered as access oriented storage devices. The critical aspect of the operation of such a hybrid AC-DC microgrid is the control strategy and power management scheme, which are very essential for providing operation in both grid connected and standalone operation modes. In microgrids, by considering control task and time scale, the management of microgrids is divided into power management and energy management. In case of power management, the objective is instantaneous management of active and reactive power based on voltage, current, power and frequency. Whereas, in case of energy management, the algorithm ensure optimal power dispatch among subgrids, considering factors such as fuel cost, capital cost, maintenance cost, mission profiles and lifetimes. The power management strategies in AC coupled hybrid microgrid are generally categorized based on operating modes such as grid connected and islanded mode. During islanded mode, the distributed generations and energy storages regulate local voltage and frequency through droop mode and using master slave method when connected to neighboring islanded microgrids. However, in grid connected mode, the power management strategies are segregated into dispatched output power and undispatched output power. The selection of power management in grid connected mode depends on the state of energy storage. If the energy storage possesses enough storage capacity, the distributed generations operate in MPPT mode, providing undispatched output power to the grid, else operate in power control mode, injecting dispatched output power. The power management strategies in DC coupled hybrid microgrid are generally categorized based on operating modes such as grid connected and islanded mode. During islanded mode, the DC coupled microgrid operates in two scenarios which requires maintaining AC bus voltage or DC bus voltage. If the microgrid requires constant DC voltage, the distributed generations and energy storage regulate the DC voltage either through droop control or power balancing. Else, while the AC bus requires constant voltage and frequency, the interlinking converter regulates the AC bus voltage. While in grid connected mode, the utility or the distributed generations and energy storage holds the responsibility to maintain DC link voltage, during which the distributed generations and interlinking converters operate in power dispatch mode respectively. The power management strategies in AC-DC coupled hybrid microgrid are generally categorized based on operating modes such as grid connected and islanded mode. During islanded mode, the power management strategy is classified into two types, which is DC bus voltage control and AC bus voltage control. The DC bus voltage will be regulated by the distributed generations and storages in the DC bus, and similarly the AC bus voltage will be regulated by the distributed generations and storages in AC bus. In one of the buses, if distributed generations fails to maintain its voltage, interlinking converter will take the responsibility to maintain the voltage. During grid connected mode, the power management strategies are further classified into dispatched output power mode and undispatched output power mode. The undispatched output power mode operates the distributed generations of both AC and DC bus in MPPT mode, while the interlinking converter regulates the DC bus voltage and the storage operates in charging mode. During dispatched power mode, interlinking converter or the distributed generation and storages in the DC bus holds the responsibility to maintain DC bus voltage, while the distributed generations and storages in AC bus provide the commanded active power to the grid operating in power control mode. The power management strategies are also categorized based on mode transition from grid connected to islanded and vice versa. While transitioning from grid connected to islanded, the power control strategy need to be shifted from the current control in grid connected mode to voltage control in standalone mode. Similarly, while transitioning from standalone to grid connected mode, the control strategy switches from voltage control to power control mode. The transitioning also requires synchronization to the grid prior to power transfer through active and passive synchronization techniques. The power and energy management techniques are broadly classified into three types, which are decentralized, centralized and distributed. The decentralized power management techniques are based on local variables and synthesized in local controllers, whereas the centralized power management techniques are based on variables from throughout the system and communication with a command center holding the global control authority. In contrary to both decentralized and centralized, the distributed technique exchange variables from neighbor entities and synthesize control quantities in local controllers. The detailed difference among centralized, decentralized and distributed power management techniques are as follows. The requirement of communication network is nil in decentralized and minimal in distributed, while the centralized techniques heavily depends on the communication network. The computation requirement of the centralized technique will be higher when compared to distributed and decentralized techniques. The accessibility to global variables exists in centralized and distributed techniques, while the decentralized technique will not be able to access them, due to which global accurate power sharing is possible in centralized and distributed techniques only. The decentralized power management majorly operate based on droop control. In hybrid AC-DC microgrids, the DC subgrids operate in voltage droop control, while the AC subgrids operate in frequency droop control. The interlinking converter, which holds the responsibility to maintain power balance among AC and DC subgrids, operate on specific droop control consisting of both AC side frequency and DC side voltage. To reduce the steady state power mismatch among AC and DC subgrids, The interlinking converters will be required to equalize the AC side frequency and DC bus voltage, synthesize required power accordingly. The control structure of a centralized control hybrid AC-DC microgrid is as shown in the figure. During centralized control, the local variable of each entity are transmitted to a higher layer called secondary layer, which generates and transmit a global variable to the local controllers. The secondary layer of multiple units transmit their local data to tertiary layer requesting global variable required to achieve optimal power management among interconnected entities. The control structure of a distributed controlled hybrid AC-DC microgrid is as shown in the figure. The requirement of distributed control over decentralized techniques arises due to unavoidable power mismatch because of dissimilar line impedance. To achieve global accurate power sharing among multiple distributed generations, storages in hybrid AC-DC microgrids, the local variables of neighbor distributed generations storages need to be transmitted through peer to peer communication. The received data can be used to adjust the local variables accordingly and achieve global power sharing. The key points from the prior description of power management techniques is that decentralized methods use local variables for control. However, due to unavailability of global variables, the method may suffer from inaccuracies in accurate power sharing. Centralized technique overcomes the inaccuracy issues, but at the cost of higher communication cost. Also it suffers from single point of failure. Distributed techniques utilizes reduced communication channels. It offers the similar performance as centralized, but with reduced cost by enabling peer to peer information exchange. In contrary to conventional architecture of hybrid microgrid, there exist other configuration such as AC-DC coupled hybrid microgrid with additional DC subgrids or AC subgrids as shown in the figure. This configuration is feasible to increase the power capacity and reliability of the system. To conclude the discussion, the hierarchical control techniques for hybrid AC-DC microgrids are utilized to improve the power balancing of single 3-phase AC microgrids and enhance the voltage quality at the point of common coupling and output terminals. The hierarchical control techniques ensure proportional active power sharing among the microgrids and helps in better utilization of the power electronics devices. The hierarchical control techniques aids to integrate futuristic systems which are locally available, diverse in nature of distributed generation. The potential research areas in the field of hierarchical control techniques for hybrid AC-DC microgrids are self-healing power systems, which ensures the stability and reliability of system during natural and man-made disasters. Cyber security of microgrids such as detection of cyber attacks, mitigation of cyber malware, investigation of cyber vulnerabilities on power sharing. We have referred almost many, but to highlight you can see the following reference which are used very frequently to prepare this study material. Perhaps you can go through these references in detail for better understanding in some of the concepts. With this note, thank you very much.